Assalamualaikum and good day everyone. My name is Firdaus bin Suhaimi and today I would like to present my PSM 1 entitled Geometry Analysis of Vehicle Suspension Linkage System. For this research, I am being supervised by Dr. Afandi Dzakaria. Okay. In this presentation, I will talk about three main parts which are introduction, literature review, and lastly methodology. So firstly, the introduction. Okay, this is my Gantt chart for PSM1, showing my planning uh, for the duration of 15 weeks, and it consists of 8 activities from project title selection until representation preparation. Okay, for the background of the study, the performance of the vehicle is not necessarily relying on the power generated by the engine only, but the suspension system also plays a big role in determining the performance of the vehicle. So researchers also been done not only to improve the performance and comfort of the vehicle, but also to ensure the safety of the driver and passengers and also the vehicle handling. The suspension system is vital to isolate the car body from the road irregular conditions and ensuring the wheels are in the correct position. Okay. There is various type of mechanism for the vehicle suspension system as shown in these four figures over here. First one we have multi-link suspension, then double wishbone suspension, and then we have McPherson strut suspension, and lastly swing arm suspension. For problem statement, apart from using commercially available multi-body simulation software, the analytical model also can be used to analyze the suspension system. However, some analytical approach does not give an accurate result. Some modification and improvement need to be made to improve the accuracy of the analytical method. So the objective of my research is to analyze the geometry behavior of the vehicle suspension linkage system. The geometry of the suspension system includes the toe, caster and camber angle. For the scope of my research is the type of suspension linkage system is McPherson strut type only, and uh, I will be developing a numerical analysis for toe, caster, and camber analysis during bump and rebound situation. Okay, for the next part is the literature review. Okay, vehicle suspension system. As you can see here, this is the McPherson strut. Okay, literally, suspension system consists of three main parts, which are spring, damper, and linkage. The spring acts as absorb and release energy, and the damper to reduce the oscillation of the uh, suspension, and the linkage acts as the holder of all the parts of the suspension and the wheel itself. And the linkage must be very strong and rigid because it need to hold other parts. So this is the McPherson strut type suspension system, and it is also known as the Chapman strut suspension, and it is most popular vehicle suspension mechanism used these days, especially in cars. Okay, this is because of its compactness and low cost. Okay, next I will talk about the toe, caster, and camber angle. Let's see the first picture here. For the camber angle, is it measured from the front view of the wheel? Okay, for the negative camber, the wheel lean inwards the vehicle, while the positive camber, the wheel lean outwards of the vehicle. For the toe angle, is measured from the top of the vehicle, as you can see here in the picture. The toe in is where the wheel lean inwards the vehicles, while the toe out, the wheel lean outwards of the vehicle. And for the toe angle must be set correctly because, as you can see here, it can affect the tire wear and also the stability of the vehicle and handling. And for the caster angle, and you need to measure it from the side of the vehicle. Okay, for a positive caster angle, it happens when the steering axle is lies toward the back of the uh, wheel or vehicle. Okay, for the negative caster angle, the steering axle leans toward the front. The greater the positive caster angles, the harder to turn the steering, but it actually helps to stabilize the wheel when speeding. Okay, for modeling of McPherson's suspension system, we have three types of modeling. First will be the quarter suspension model. And you and Chu use this quarter model over here to compare the difference of the output given by the linear, nonlinear, linearized, nonlinear, and the Adams quarter suspension model. Okay, based on his findings, the nonlinear and linearized nonlinear model produce more accurate result when compared to Adams model, while the linear model is not so accurate. Okay. For the quarter suspension model are also used to optimize and determine the design sensitivity of the suspension. This is done by Lee and his friend. The system it was modeled as simple joints and links of kinematic foundation and assumed to be rigid bodies where the friction are negligible. Okay, next we have half suspension model. As you can see here, half suspension model means that it consists of two sets of suspension, which are either a front or the rear part of the car. Since it involves two sets of the suspension system, more information can be obtained from the model. And the nonlinear and linearized nonlinear half suspension model shows the same result in the Adams half model. Okay, lastly, we have the full suspension model. As you can see here, this is exactly the representation of the suspension in a car, the four sets of suspension system, which is U and 2 again, presented this model over here to use as a reference to validate the other models previously. Okay, the full suspension model will give a more accurate and realistic result as it consists of all suspension system in a car, which is four. Okay, for the geometry analysis of vehicle suspension linkage system, Debari used 2D model of Dacia Logan suspension system to perform the kinematic and dynamic analysis. And based on his findings, the differences between the result obtained from the analytical method, which is matrix method over here, is below 5% when compared to the 3D model. Hurrell, with his friend, also conducted a kinematic and dynamic analysis using a planar quarter car model, which is the 2D model as well. Okay, Lee used the matrix method to improve the design of the suspension in terms of drive quality and steering stability. And lastly, we have Rankinen and his friends used the displacement matrix method to validate a nonlinear 2D model of the McPherson suspension system. So the kinematic analysis in his research does not show any significant difference, while for the dynamic analysis, the camber angle shows a very significant difference. This is caused by the simplification of the equation in the mathematical model. Okay, next we have the second method to analyze the geometry, which is polynomial equation method. Kodati and his friends studied the geometry of the suspension in full complexity. So the purpose of his research was to improve the existing methods because the existing method unable to provide the possible solution without the initial guess or setup parameters. And next we have a rectangular Cartesian coordinates method, which was done by Attia. He used this method to simplify and improve the accuracy of the suspension analysis. His suggested algorithm eliminates the need to write the redundant constraints and allows solving a reduced system of equation. Okay, lastly, we have a vector method, which is done by Patil. He proposed a vector method in his paper, and his method can be easily executed using Microsoft Excel, as you can see here, a sample. the picture I put here. The result obtained from the analytical calculation were then compared and validated by the Pro mechanism software. And the both models gave the same result, which made it possible to use the proposed method to generate or optimize the suspension system in terms of camber and caster angles. This the execution in Microsoft Excel is very good when the designers are unable to subscribe or buy the multi-body software. Okay, that's all for my literature review. Then I will proceed to the methodology. Okay, this is the flowchart of my methodology, which is the flow of my research. First, I will go to the introduction and then literature review. And for the modeling, there will be two parts, which are the 3-point method, which is a vector method actually using MATLAB modeling. And then we have MSc Adams, which is a multi-body uh, system software. After running the numerical analysis, I will compare the result between these two models over here. If there are significant difference, then I will go back to check on the 3-point method here. Okay, for my research, I will be using a quarter model of MacPherson Strat. Okay, as you can see here, it have all the labeling here, and this is the table is the position of the points in XYZ plane, okay, for A, B, C until J. And this data is extracted from the textbook titled The Multibody System Approach to Vehicle Dynamics. So let's say the suspension hitting a bump, the strategy will compress, which changing the location of the point DG. So there are some of other points that affected as well. So to conduct the vector 3-point method, there are sequence of calculation that need to be followed, which are to locate the point C first, and then we locate point E, G, I, J, and lastly H. Okay. Okay. To locate the points, we are required to have this initial data, which is the position in the XYZ plane, and then the magnitude or the length of the uh, between 2 points. Okay, so for example, to locate the point C, okay, let's say there are 4 points A, B, C, and D, where A, B, C, A, B, D are known, and the position of point C need to be determined, which is over here, which is A, B, D are all known, and then we know the length of CA, CB, and CD. So to obtain the components of CX, CY, and CZ, the three equation below is set up. 1, 2, 3. Okay, and then we expand the equation, producing equation 4, 5, and 6, and we substitute the initial values above into the equation 1, 2, 3, and expand the equation to obtain like this. Okay, then we simplify the previous equation, and after simplifying the equation, we subtract equation 7 with equation 8, and we got Cx, which is 5 mm. And then we take subtracting equation 8 with 9, result in this equation. After that, we substitute the expression into equation 11 to obtain this cy in terms of cz's. After that, we substitute expression 12 and 10 into equation 7 to produce this quadratic equation, equation 13. And rearranging the quadratic equation, we can solve using this formula over here, and we obtain Cz, which is two values over here, 56.496 millimeter and negative 88.697 millimeter. The two possible solutions show that this geometric analysis is nonlinear. So we input the values into equation 12 to obtain Cy, which is these are the values. And lastly, we found all the position vector of point C, which is actually has two set of values over here. This shows that the solution is nonlinear, and a logical conclusion is needed to determine the value that will be used. In this case, the position of position C is like this. And this process of vector 3-point method is repeated to find point E, G, I, J, and H. So to determine the toe, caster, and camber angle, uh, we are actually interested in the I and J only position, the position of I and J only. The formula is actually all the same, but the uh, condition is different over here. For the toe angle, the Z coordinates of the points are set to be 0. And for the caster, the Y coordinates are set to be 0. And for the camber angle, the X coordinate are set to be 0. So to conduct the MATLAB, the vector 3-point method, I use MATLAB. Okay, when the strut DG is assumed to compress about 100 mm when hitting a bump, so the movable points can be determined for every 10 millimeter decrement of length strut DG just now. So after that, we can obtain the toe, caster, and camber angle based on the decrement. And the magnitude of all the 12 lengths can be obtained by conducting a measurement on the model in the SolidWorks. This is the initial data required. So I will conduct a measurement in SolidWorks so that I can get the initial values. From every 10 mm compression of strut DG, the 12 lengths can be obtained and graphs can be plotted to determine the relationship between the lengths. And lastly, to validate my result, I will model my suspension in MSc Adams software, which is well known for its multi-board dynamics and motion analysis software. Uh, this software can straight away give me the value for toe, caster, and camber angle, and also some other kinematic and dynamic analysis also. The value obtained from this software, they will then compare to the MATLAB, and if there are any difference, then I will check back with the MATLAB modeling. Okay, these are my references, which have 17 of them, and I think that's all from me. Thank you for watching.